Welcome to The Explainer. Today, we are diving deep into the secret life of numbers. We're going to find the hidden building blocks, the atoms, that make up, well, everything. From the way we count to the secret codes that keep our digital lives safe.
So believe it or not, our journey starts with a kid's counting game. And it involves two really popular Indian snacks, idli and vada. And somehow, there's a mathematical pattern hidden inside that connects them all. How cool is that?
Right, so this game is called Idli Vada, and it's actually a super clever way to get at a really big idea in math.
Okay, the rules are pretty straightforward. You just count up from 1. But instead of saying a multiple of 3, you say idli. And instead of a multiple of 5, you say vada. So it goes something like 1, 2, idli, 4, vada, idli. You get the picture. But the real fun, the real magic happens when a number is a multiple of both 3 and 5.
So, the very first time you have to shout idli vada is when you get to the number 15. The next time, it's 30. And after that, 45. See that pattern emerging? These special numbers, the ones where both rules kick in at the same time, they're the key to this whole thing.
And this simple game, it's a perfect illustration of what mathematicians call common multiples. They're just numbers that share a property. In this case, they're multiples of both 3 and 5. You can almost think of them like shared stops on a bus route, or shared destinations on the number line. All right, so let's completely flip this idea around. Instead of building numbers up, let's see what happens when we start breaking them down. So, instead of taking jumps of a certain size to see where we land, let's imagine there's a treasure chest waiting for us at a specific number. The new game is to figure out all the different jump sizes we could use to land exactly on that treasure. Let's call this the jump jackpot game. So imagine the treasure is on the number 24. If you pick a jump size of, say, 4, you'd go 4, 8, 12, 16, 20, and then boom, 24. Jackpot, you win. And it turns out there are a bunch of winning jump sizes for 24. Jumps of 1, 2, 3, 4, 6, 8, 12, and even 24 itself all land you right on the treasure. You know these winning jump sizes? They actually have a proper mathematical name. We call them factors. And all a factor is a number that can divide another number perfectly with absolutely no remainder. Okay, so this whole idea of factors, of breaking numbers down into smaller pieces, it actually leads us to a much deeper, more fundamental question. It makes you wonder, are there some numbers that you just can't break down at all? Numbers that are, unbreakable. Here's a way to think about it. Say you have 12 figs. You could arrange them in a nice little 2x6 rectangle or a 3x4 rectangle. You've got options. But what if you only have 7 figs? Well, your only choice is a single row of 7. That's it. This difference in how you can arrange them, which is really just about how many factors a number has, it points to this huge divide in the world of numbers. And this is that fundamental split I was talking about. Numbers like 7, the ones you can't really arrange, they're called prime numbers. They only have 2 factors, just 1 and the number itself. But then you have numbers like 12 with more than 2 factors. We call those composite numbers because they are literally composed of other smaller factors. So what about the number 1? Well, 1's kind of special. It only has 1 factor, itself. So it doesn't really fit into the prime or the composite camp. It's in a league of its own. Okay, so now we know what primes are, but how would you actually find them? Like, say you wanted to find all the prime numbers up to 100. How would you do that without checking every single one?
Well, for that, we can turn to an absolutely brilliant method that's over 2,000 years old. It was invented by a Greek mathematician named Eratosthenes, and it's called a sieve, which is the perfect name because it literally lets you filter out all the composite numbers and just keep the primes.
Here's the gist of how it works. First, you get rid of 1, because we know it's not prime. Then you circle the very first prime number, which is 2. And once you've circled 2, you go through your list and cross out every single multiple of 2, all the even numbers. Because if it's a multiple of 2, it can't be prime, right? So they're gone. Now, you look for the next number on your list that isn't crossed out. That would be 3. So we circle it. That means it has to be a prime number.
And then we do the exact same thing again. We go through and cross out all the remaining multiples of 3. Some of them, like 6, are already gone, but we'll catch the ones that are left, like 9, 15, 21, and so on.
And you just keep doing that. You find the next uncrossed number, circle it, and then cross out all of its multiples. You do this for 5, then 7, and so on. And what happens is you systematically filter out all the composite numbers. The only numbers left standing, the ones that are circled, are the prime numbers. It's such an elegant and really a powerful way to find these fundamental building blocks.
So, great, we found all the primes. But so what? Why are they so important? Well, it's because they aren't just special numbers. They are literally the building blocks, the Lego bricks of all other numbers. Here is the big, mind-blowing idea. Any composite number, no matter how big, can be written as a product of prime numbers, and that specific set of primes is unique to that number. It's called its prime factorization. You can think of it like a number's unique DNA. And this secret code isn't just a mathematical curiosity. It's the foundation of modern cryptography. It's easy to multiply two large primes together, but incredibly difficult to take that resulting giant number and find the original primes. That one-way difficulty is what secures everything from your bank account to your private messages.
Let's try it with the number 36. You could start by splitting it into, say, 4 times 9. But wait, neither 4 nor 9 is a prime number, right? So we have to keep going. We can break 4 down into 2 times 2, and we can break 9 down into 3 times 3. Now look at what we have. 2, 2, 3, and 3. All of those are prime numbers. We can't break them down any further. That's it. That's the prime code for 36. 2 2s and 2 3s. And here's what's so amazing. It doesn't matter how you start. You could have broken 36 down into 6 times 6 or 2 times 18. It makes no difference. No matter which path you take, you will always end up with the exact same list of prime factors, 2 2s and 2 3s. This powerful, unbreakable rule is so important it's called the fundamental theorem of arithmetic. It's a true cornerstone of all math. For literally thousands of years, prime numbers have totally captivated mathematicians. And even though we figured out so much, they still hold these deep, deep mysteries that people are trying to solve right now. The search for bigger and bigger primes is this huge global effort that's always going on. And the scale of what we found is just mind-boggling. Get this, the largest prime number we know of today is so massive that if you wanted to write it all out, you'd need a book that's about 6,500 pages long just to write down one number.
And all of this leads to one final huge question. Is there a point where it all stops? Is there a largest prime number out there waiting at the end of the line? Or does the list of primes just go on forever? Now, the answer to that question has actually been known since ancient Greece. But knowing the answer doesn't stop the wonder. It just makes us appreciate this endless, beautiful, hidden structure within the world of numbers. A structure that doesn't just describe our universe, but as we saw, is also working behind the scenes to protect our world within it.